An aneurysm is a bulge in a blood vessel. Most aneurysms do not cause symptoms, but a ruptured aneurysm can be life-threatening. Symptoms of a ruptured aneurysm can include, firstly, sudden severe headache, secondly, stiff neck, thirdly, nausea and vomiting, fourthly, confusion or loss of consciousness, fifthly, vision changes, sixthly, weakness or numbness on one side of the body, and seventhly, seizures. In your scenario, where the generator neutral is bonded to the generator frame and the system is designed to intentionally tie the generator and solar power supplies together, there are some considerations to make. Typically, the generator neutral should be bonded to ground at the generator itself, and the neutral should be switched in the ATS to maintain proper grounding. However, in this case, since the neutral is intentionally tied together, the grounding bond can be located in the proximity of the inverter battery room. The ATS should ideally switch both the live and neutral conductors. If the neutral is not switched, it is possible for current to flow through the generator even when it is not powering the house. This could create a safety hazard if the generator is not properly isolated. You should consult with the solar installer to confirm the operation of the ATS and the wiring configuration. It is crucial to ensure that the system is properly installed and meets electrical safety standards. Based on your description, it seems that the ATS may not be a conventional transfer switch but rather a disconnect. In this case, you need to determine the specific wiring and operation of the system to ensure that it is functioning properly and safely. It is important to note that electrical work can be dangerous and should only be performed by qualified individuals. If you are not comfortable working on the electrical system yourself, it is recommended to hire a licensed electrician to assist you. Considering your generator is accompanying a solar system for a house, with the neutral bonded to the frame, and you're installing a disconnect for the generator, it's crucial to understand the grounding and neutral switching implications. The primary concern revolves around whether the automatic transfer switch, or ATS, switches the neutral and the potential for objectionable current. If the supplies, generator and solar, are intentionally tied together, traditional grounding methods require careful consideration. Typically, with a generator bonded neutral to ground, the neutral must be switched in the ATS. The question arises whether there's an opportunity for objectionable current if the neutral isn't switched. In this specific setup, it might seem like an extension of the same system. Ideally, the neutral or grounding bond should be located near the inverter or battery room, and the bond at the generator could be removed, if feasible. Whether the neutral is switched becomes less critical in this configuration. However, given the complexity of the system with inverters, the ATS, controllers, and other electronic components, it's essential to verify the ATS operation. It's recommended to consult with the solar installer to determine the switch operation. Here's a breakdown of the key considerations. Firstly, grounding and bonding. The purpose of grounding and bonding is to create a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. In a typical system, the neutral conductor is bonded to ground at the service entrance. Secondly, generator grounding. When a generator is used as a separately derived system, it usually requires its own grounding electrode system. This means the generator's neutral is bonded to the generator frame, which is then connected to a grounding electrode, such as a ground rod. Thirdly, transfer switch operation. A transfer switch is used to switch the load between the utility power and the generator. In many cases, the transfer switch also switches the neutral conductor to avoid creating parallel neutral paths. Fourthly, objectionable current. Objectionable current can flow on grounding conductors if there are multiple ground paths. This can occur if the neutral is bonded to ground at multiple locations, such as both the service entrance and the generator. Fifthly, solar system considerations. Solar systems often include inverters that convert DC power from the solar panels to AC power. These inverters may have their own grounding requirements, which must be coordinated with the generator and service entrance grounding. Sixthly, NEC requirements. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. It's crucial to adhere to these requirements to ensure safety and proper operation. Seventhly, your specific scenario. In your case, where the generator and solar system are intended to be tied together, it's important to understand how the ATS is wired. If the ATS does not switch the neutral, there could be a potential for objectionable current. Eighthly, recommended approach. Consider moving the neutral ground bond to the proximity of the inverter or battery room. This could simplify the grounding scheme and reduce the risk of objectionable current. However, this approach must be carefully evaluated to ensure it meets all applicable codes and standards. Ninthly, verify ATS operation. Contact the solar installer to determine how the ATS switches the conductors. This information is crucial for understanding the grounding implications. Tenthly, professional consultation. Given the complexity of the system, it's highly recommended to consult with a qualified electrician or electrical engineer. They can assess the system, verify compliance with codes, and recommend the best grounding and bonding strategy. Neutral switching is a critical aspect of generator and solar system integration, particularly when these systems are intended to operate in parallel or with shared loads. The function of neutral switching is to prevent multiple neutral to ground connections within the system, which can lead to objectionable ground currents and potential safety hazards. Firstly, preventing parallel neutral paths. When a generator is connected to a system that already has a neutral to ground bond, such as at the main service panel, a parallel neutral path is created. This means that neutral current can flow through both the intended neutral conductor and the grounding conductors, including equipment grounds, conduit, and even the earth. This parallel path can result in several problems, including secondly, objectionable ground current. Current flowing through grounding conductors can cause electromagnetic interference, voltage drops, and even pose a shock hazard. Ground current can also interfere with sensitive electronic equipment. Thirdly, safety hazards. If a fault occurs in the system, such as a short circuit from a live conductor to ground, the fault current may not follow the intended path back to the source if there are multiple ground paths. This can reduce the effectiveness of overcurrent protection devices, such as circuit breakers and fuses, and increase the risk of electrical shock. Fourthly, code compliance. Electrical codes, such as the National Electrical Code, or NEC, typically require that there be only one neutral to ground connection in a system. This is to prevent the creation of parallel neutral paths and the associated hazards. Fifthly, transfer switch operation. To avoid multiple neutral to ground connections, a transfer switch can be used to switch the neutral conductor along with the phase conductors. When the generator is connected, the transfer switch disconnects the neutral from the main service panel and connects it to the generator's neutral to ground bond. Sixthly, types of transfer switches. There are two main types of transfer switches. Firstly, non-switch neutral transfer switches. These switches only switch the phase conductors and leave the neutral connected to the main service panel. These types of switches are generally only suitable for systems where the generator is not intended to operate in parallel with the utility power. Secondly, switch neutral transfer switches. These switches switch both the phase conductors and the neutral conductor. These types of switches are required for systems where the generator is intended to operate in parallel with the utility power or where there is a risk of multiple neutral to ground connections. Seventhly, generator grounding. When using a switched neutral transfer switch, the generator must have its own neutral to ground bond. This bond is typically located at the generator and consists of a bonding jumper connecting the neutral conductor to the generator frame. Eighthly, solar system integration. When integrating a solar system with a generator, it is important to consider the grounding and bonding requirements of both systems. In some cases, it may be necessary to use a switched neutral transfer switch to avoid multiple neutral to ground connections. Ninthly, considerations for your system. In your specific scenario, where you have a 12 kilowatts generator accompanying a solar system for a house, it is important to determine whether the automatic transfer switch or AT switches the neutral. If the ATS does not switch the neutral, you may need to consider upgrading to a switched neutral ATS or modifying the grounding and bonding configuration to ensure compliance with electrical codes and to prevent objectionable ground currents. Tenthly, professional consultation. Given the complexity of grounding and bonding requirements, it is always recommended to consult with a qualified electrician or electrical engineer to ensure that your system is safe and compliant with all applicable codes and standards. Neutral switching in generator and solar systems is crucial for safety and code compliance. By preventing parallel neutral paths, neutral switching helps to minimize objectionable ground currents and reduce the risk of electrical shock. Always consult with a qualified professional to ensure that your system is properly grounded and bonded. Considering the presence of inverters, controllers, and other electronic devices, a traditional approach of simply turning through to check if the ATS switches the neutral may not be reliable. Electronic components can sometimes provide unexpected paths for signals, leading to inaccurate results. Therefore, a more methodical and comprehensive approach is required. Here are some steps that can be taken to accurately determine the ATS neutral switching operation. Firstly, documentation review. Obtain and carefully review the documentation for the ATS, inverters, and other relevant equipment. This documentation should provide information on the wiring configuration, grounding requirements, and switching operation of the ATS. Secondly, visual inspection. Conduct a thorough visual inspection of the wiring connections at the ATS, generator, and main service panel. Look for any signs of improper wiring or modifications. Pay close attention to the grounding and bonding connections. Thirdly, continuity testing with power off. With the power completely off and all sources of energy disconnected, use a multimeter to perform continuity tests. Check for continuity between the neutral conductor at the generator and the neutral conductor at the main service panel when the ATS is in different positions, utility power and generator power. This can help determine if the neutral is switched. Fourthly, voltage testing with power on. Carefully perform voltage measurements with the power on, following all safety precautions. Measure the voltage between the neutral conductor and ground at various points in the system, such as at the generator, ATS, and main service panel. This can help identify any potential ground loops or objectionable current. Fifthly, load testing. Perform load testing of the system with both utility power and generator power. Monitor the voltage and current at various points in the system to ensure that the system is operating properly and that there are no signs of excessive ground current. Sixthly, professional inspection. Consider hiring a qualified electrician or electrical engineer to perform a professional inspection of the system. They have the knowledge and experience to identify potential problems and ensure that the system is safe and compliant with all applicable codes and standards. When dealing with complex electrical systems involving generators, solar power, and electronic components, it is essential to take a comprehensive approach to ensure safety and proper operation. Relying solely on simple methods like turning through may not be sufficient. Always prioritize safety and consult with qualified professionals when necessary. The operation of the automatic transfer switch, or ATS, is critical for ensuring the safe and reliable transfer of power between the utility grid and the generator. There are several methods to determine the specific operation of the ATS, each with its own advantages and limitations. The most effective approach often involves a combination of these methods. Firstly, visual inspection and tracing wiring. Carefully examine the wiring connections at the ATS, generator, and main service panel. Trace the wiring of the neutral conductor to see if it is switched by the ATS. Look for any markings or labels on the ATS that indicate its switching configuration. Secondly, reviewing the ATS documentation. Obtain the manufacturer's documentation for the ATS. This documentation should provide detailed information on the ATS operation, including whether it switches the neutral conductor. Look for wiring diagrams and technical specifications. Thirdly, using a multimeter to test continuity. With the power completely off, use a multimeter to test the continuity between the neutral conductor on the utility side and the neutral conductor on the generator side of the ATS. Perform this test with the ATS in both the utility and generator positions. If there is continuity in both positions, the ATS does not switch the neutral. If there is continuity in only one position, the ATS does switch the neutral. Fourthly, using a multimeter to measure voltage. With the power on, carefully measure the voltage between the neutral conductor and ground at various points in the system. This can help identify any potential ground loops or objectionable current. However, this method should be used with caution, as it can be dangerous if not performed correctly. Fifthly, observing the ATS operation during a power outage. If possible, observe the operation of the ATS during a simulated or actual power outage. See if the neutral conductor is disconnected from the utility grid when the generator is running. Sixthly, consulting with the solar installer. Contact the solar installer who installed the system. They should have detailed knowledge of the ATS operation and wiring configuration. They may also be able to provide documentation or technical support. Seventhly, hiring a qualified electrician. If you are not comfortable performing these tests yourself, hire a qualified electrician to inspect the system and determine the ATS operation. They have the knowledge, experience, and equipment to perform these tests safely and accurately. When determining the operation of an ATS, it is important to consider safety precautions. Always disconnect power before performing any tests. Use appropriate personal protective equipment, such as gloves and eye protection. If you are not comfortable working with electricity, hire a qualified electrician to perform the tests for you. By using a combination of these methods, you can accurately determine the operation of the ATS and ensure that the system is safe and reliable. Remember to prioritize safety and consult with qualified professionals when necessary. When evaluating the grounding and bonding requirements for a generator integrated with a solar system, you must consider several key factors outlined in the National Electrical Code, or NEC. These requirements are designed to ensure electrical safety and prevent hazards such as electric shock and fire. Here is a breakdown of the relevant NEC sections and considerations. Firstly, NEC Article 250 Grounding and Bonding. This article provides the general requirements for grounding and bonding electrical systems. It covers topics such as grounding electrode systems, equipment grounding conductors, and bonding of metal parts. Secondly, NEC Section 250.20 System Grounding. This section specifies when electrical systems must be grounded. In general, alternating current, or AC, systems operating at 50 volts or more must be grounded. Thirdly, NEC Section 250.30 Grounding separately derived AC systems. This section applies to generators and other sources of power that are not directly connected to the utility grid. It requires that these systems be grounded in accordance with specific rules. Fourthly, NEC Section 250.30 A Grounding Electrode System. This section requires that separately derived systems have a grounding electrode system that is connected to a grounding electrode, such as a ground rod or metal water pipe. Fifthly, NEC Section 250.30 A One Bonding Jumper. This section requires that the neutral conductor of the separately derived system be bonded to the equipment grounding conductor at the source of the system, such as at the generator. Sixthly, NEC Section 250.32 Buildings or structures supplied by a feeder or branch circuit. This section applies when a building or structure is supplied by a feeder or branch circuit from another building or structure. It requires that the grounding electrode system at the second building or structure be connected to the grounding electrode system at the first building or structure. Seventhly, NEC Section 705.16 Point of Connection. This section applies to interconnected electric power production sources, such as solar systems. It requires that the point of connection between the power production source and the utility grid be clearly marked. Eighthly, NEC Section 690 Solar Photovoltaic PV Systems. This article provides specific requirements for grounding and bonding solar systems. It covers topics such as equipment grounding, system grounding, and ground fault protection. Ninthly, NEC Section 690.41 Grounding. This section requires that solar systems be grounded in accordance with Article 250. It also provides additional requirements for grounding specific types of solar equipment. Tenthly, NEC Section 690.43 Equipment Grounding Conductor Size. This section specifies the minimum size of the equipment grounding conductor for solar systems. The size of the equipment grounding conductor must be based on the overcurrent protective device protecting the circuit. 11th, considerations for your system. In your case, where you have a generator integrated with a solar system, it is important to ensure that both systems are properly grounded and bonded. The generator must have its own grounding electrode system, and the solar system must be grounded in accordance with Article 690. The neutral conductor of the generator must be bonded to the equipment grounding conductor of the generator. 12th, professional consultation. Given the complexity of grounding and bonding requirements, it is always recommended to consult with a qualified electrician or electrical engineer to ensure that your system is safe and compliant with all applicable codes and standards. Proper grounding and bonding are essential for electrical safety. By following the requirements of the National Electrical Code, or NEC, you can ensure that your generator and solar system are properly grounded and bonded, reducing the risk of electrical hazards. Always consult with a qualified professional to ensure that your system is safe and compliant.